So before we continue with the session, let's briefly discuss if you had some time to think about this. So any thoughts on which of the two sketches depict the right interface between two different Chern insulators, with Chern number 1 and Chern number 2? Yes, right, wonderful. So yeah, the right interface between the two Chern insulators is the one that appears on the right, because of course the number of H states that you have is just the difference between the Chern numbers between the left and the right. All right, great. So in the following, let's try to understand a little bit what is the mathematical structure of the Landau levels, and in particular, see how the spectra gets modified when we apply magnetic field. So something that is actually very interesting to notice is that there's going to be a really, really big difference between the Landau levels of graphene and the Landau levels of some other two-dimensional electron gas, such as, let's say, MOS2 and so forth. And the basic idea is that this radical difference comes just from the electronic dispersion. So as you go from a linearly dispersing gas to a Dirac dispersing gas, the dependence of the energy scale of the Landau levels with the magnetic field is completely different. So in particular, for a two-dimensional conventional electron gas, as what we have at the gamma point in TMDCs, the typical energy scales that we have for Landau levels, namely the energy spacing, is something like 1 MeV if you go up to, let's say, 10 Teslas or so. Whereas in the case of graphene, the energy scale is much, much bigger. And the reason for this is just that the energy scale depends linearly on the magnetic field in the case of two-dimensional electron gases, but it depends with the square root for Dirac equations. And this is just a direct consequence of what is the dispersion of your electronic system. If your dispersion is quadratic, then your Landau levels are going to depend linearly. If your dispersion is linear in the momentum, and in particular you have a Dirac equation, then the energy scale is going to go with the square root. So what this actually allows is that in graphene, you can see quantum Hall effect at much, much higher temperatures and much, much lower magnetic fields than in other two-dimensional electron gases. And in particular in graphene, you can even see quantum Hall effect at room temperature. So an effect that's many decades ago, it was believed to appear only at really, really low temperatures. All right, so let us now look at the mathematical structure of the Landau levels, and for that, we need to take a very specific gauge for our magnetic potential. And as I mentioned before, we are going to be working all the time with the Landau gauge, which is this gauge that only breaks translational symmetry in one direction. But of course, there are many other gauges, and in particular, the symmetric gauge, it is very useful for understanding fractional quantum Hall states. So from now on, our gauge is going to be this one. So we break translational symmetry in one of the directions, not in the other one. And of course, when you compute the curl of this gauge potential, we obtain our previous magnetic field. So the basic idea to understand Landau levels is that you just have to do the minimal coupling. And if you think about the kinetic energy in a continuum model, what this actually means is that instead of just having the momentum, you have the momentum plus your potential. Now this potential has a certain dependence in space because you have to choose a specific gauge. And the basic idea is that this is just a, let's say, differential equation that we are actually extremely used to deal with. So since your magnetic potential was, let's say, linear in one of the coordinates, once you make the replacement in a Hamiltonian that is, for example, quadratic, you are going to get terms that are quadratic in the momentum and quadratic in the position. And this type of Hamiltonian, in which you have p squared and x squared, or p squared and y squared, is just a harmonic oscillator. So essentially, Landau levels are just harmonic oscillator levels of a two-dimensional electron gas when you apply a magnetic field. And since they are harmonic oscillator levels, then you can directly see that they are going to be linearly proportional to the magnetic field, and that the energies that you are going to get for Landau levels are just, let's say, equally spaced energies that are indexed by an integer n. So in short, to compute Landau levels, you just have to solve a harmonic oscillator for a conventional 2D electron gas. So now if you take, for example, the electronic structure of the gamma point of the transition metal dichalcogenide, then what you actually see is that if you start at 0 magnetic field for a ribbon of your TMDC, you have many, many bands, which are the different bands of your TMDC. And now as you start adding a bigger and bigger magnetic field, you essentially see that you start developing flat bands that have a equally space between them. And this spacing is, of course, the energy scale of the Landau levels. And eventually, once you are at large enough magnetic fields in comparison with the width of your ribbon, you see that you have regions in momentum space with very flat bands and an energy spacing that is constant in between all of them. So essentially, you see that from the results of a die banding model, you essentially recover the result that you have from a continuum model for the Landau levels. All right, great. So that was for conventional two-dimensional electron gases, and in particular for 2D materials that don't have a Dirac dispersion. Now let us focus on graphene that does have a Dirac dispersion. So again, what we are going to do from the point of view of the continuum limit is we are going to just take Dirac equations at the k and k prime point and understand everything just from those Dirac equations coupled to a magnetic field. So for the Dirac equation, you do exactly the same idea. You start with your Hamiltonian that just depends on momentum and that you have off diagonals in the momentum. You make the canonical replacement with the specific gauge that you chose to take, which is, for example, Bx. And now when you make that canonical replacement, you start having terms with x in your off diagonals of the Hamiltonian. Now you have to compute the eigenvalues of this Hamiltonian, right? And now it is not so easy because now you have a matrix instead of just a single differential equation. But the actual trick here is to just compute the square of your Hamiltonian. And when you compute the square of the Hamiltonian, the square becomes diagonal. And once it is diagonal, you can solve it. So in particular, once you compute the square of the Hamiltonian, you see that the square of the Hamiltonian now is a harmonic oscillator. For a conventional 2D electron gas, the Hamiltonian was a harmonic oscillator. For a Dirac electron gas, the square of the Hamiltonian is a harmonic oscillator. What this actually means is that your eigenvalues are now going to depend on the square root of the magnetic field instead of depending just on the magnetic field alone. So when the Hamiltonian was a harmonic oscillator, you had a B dependence. When the square of the Hamiltonian is a harmonic oscillator, you get the square root of B dependence. And this is the simple reason why for Dirac electrons, and in particular for graphene, the dependence on the magnetic field is different as for conventional electrons. And of course, you can also see this if you just take a tie banding model for graphene and couple your magnetic field using the substitution that we discussed before. And essentially what you see is that if you take a ribbon and you apply a certain magnetic field, you get a set of flat bands and a set of edge states, which are of course the edge states of the quantum Hall state, but now they are not equally spaced. Right now, the spacing between the first and the second is different than from the second and the third, just because now you have a square root of n b. So, and this square root of n essentially makes your spacing different as you may go to bigger and bigger n. So this is, of course, something that you also recover from the tie banding model. And now let us look at how the density of states evolves with magnetic field. And this may remind you something that we actually saw in the previous session. So if you start with the density of states of graphene, you get a V-shaped density of states. And now if you start increasing more and more your magnetic field, you start developing singularities in your density of states. And it was actually very, very similar to what we observed in the previous section, that as we change the Moiré pattern of a system, we start developing more and more Van Hoff singularities. So this is also another way of understanding that a magnetic field is like a quasi-periodic potential. The quasi-periodic potential also created Van Hoff singularities as we were increasing it and as we were changing its wave vector. And the magnetic field also creates this Van Hoff singularity. So this relates again to this mapping between quasi-periodicity and quantum Hall states. Magnetic field in quantum Hall states give rise to Van Hoff singularities coming from the Landau levels. Quasi-periodicities give rise to Van Hoff singularities coming from your different, let's say, minibands and in the incommensurate limit from the different gaps that develop in your spectra. All right, now there's also something very interesting to notice here. So in all the sessions before, we were saying, well, monolayer graphene is not a great material for having correlations just because the density of states is V-shaped, right? But now when you apply a magnetic field, you suddenly get a huge enhancement of the density of states at zero energy. So in zero magnetic field, there's in principle no electronic instability at very small interactions, just because the density of states is zero. But as you make your magnetic field bigger and bigger and bigger, your density of states also becomes bigger and bigger and bigger. So magnetic field in graphene can actually drive an electronic instability. And once again, this is also very similar to the effect of Moire patterns, right? We also saw that if we don't have a Moire pattern, we may not have an electronic instability. But if we add a Moire pattern, we can drive an electronic instability. So this is, again, just another reflection of this mapping between magnetic fields and quasi-periodicity. Yeah.
I use a lot of analogy a lot because I didn't think about it this way. But so the fact that in this case it's topological, and in Moire case it's not. It doesn't need to. It comes from the vectorial form of this transformation, like the fact that you have a name which is in Z, or and instead of Moire is like not directional. Is it related to this? Let's say, what's the point that gets to the topological aspect?
That's a very good question. And the point is that the Moire patterns are actually topological quite often. So the gaps that you open in Moire patterns are many times topological. They are topological in a slightly different way. So many times the Moire minibands, they create edge states by themselves, which are a reflection of the edge states of this high dimensional quantum Hall state. Let's say we usually don't think too much about them. So we just usually think about the Moire minibands created by the Moire pattern, but very often the gaps that appear from your Moire pattern is actually topological by itself.
So it's like the triangular,
yeah. Yeah. It's
constant.
Yeah, absolutely. But let's say if you think in terms of how the magnetic field looks like when you Fourier transform in one direction, you actually see that you also have a length scale associated to the magnetic field, right? Which is this length scale in which this cosine was oscillating, right? So that is essentially how the Moire pattern of the magnetic field appears when you do the transformation. Yeah, and so really with that point, of course, the Landau levels are topological, and also very often the flat bands that we have in Moire materials are topological. That will become important later on. All right, so now let us look at how the electronic spectra of a graphene looks like as we increase the magnetic field. So here on the left, you have a ribbon in which we don't have any magnetic field, so the density of states is very, very low. And there's a small gap because the ribbon has a finite width. And then as you increase the magnetic field more and more and more, you see that you start developing these flat bands at zero energy, flat bands at the charge neutrality point, flat bands where you didn't have a states before adding a magnetic field. And of course, the larger your magnetic field, the bigger the portion your flat bands occupy in reciprocal space, and therefore the stronger your potential electronic instability is going to be. So actually something that is extremely important from graphene is that the Landau levels are actually very special in a sense that apart from having a certain, let's say, mathematical form in real space, they also have an internal sublattice structure, an internal spinor structure that it's inherited from the sublattice degree of freedom. So in graphene, you have two sides per unit cell, and therefore the Landau levels are also going to have a spinor degree of freedom. And this spinor degree of freedom essentially relates to sublattice A or sublattice B. And in particular, the zeroth Landau level, the Landau level that appears at charge neutrality, is actually fully sublattice polarized. What this actually means is that the eigenfunctions can live either fully in one sublattice or they can live fully in the other sublattice. And what this actually allows you to do is to essentially create symmetry broken states very easily. So for example, if you want to just fill electrons in one of the sublattices, you can just fill one of the Landau levels and not the other one. If you want to fill, for example, up electrons in sublattice A, and down electrons in sublattice B, you can also do it directly on the Landau levels. So sublattice is a degree of freedom that is diagonal in the lowest Landau level. And in particular, if in the absence of interactions, all the Landau levels are degenerate, once you are at half filling and you allow for interactions, 2 Landau levels may get filled and 2 Landau levels may get empty. And now the idea is that, of course, Landau levels, they have a Chern number, right? So depending on how you reshuffle these Landau levels, you may have something that has Chern number equal to 0, or Chern number equal to 0, different from 0, or Chern number, positive Chern number for spin up, negative Chern number for spin down, and so forth. So all the different combinations. So in graphene, once you apply magnetic field and you start adding different perturbations, like, for example, an in-plane magnetic field, or you align your HBN in the substrate with your graphene to induce a sublattice balance, you can essentially go in between these different symmetry broken states in which you fill 2 Landau levels and you leave empty the other 2 Landau levels. All right, and now let me show you a specific example of that. So here we are taking again our graphene ribbon, and what I'm doing is I am essentially putting by hand a symmetry breaking term that fills 2 of the Landau levels and leaves the other 2 Landau levels empty. And in one of the cases, I am allowing for a breaking of inversion symmetry, namely that all the electrons go to one sublattice and the other sublattice is empty. And in this situation, what you see is that there's a full charge gap. So there's a correlated state in graphene monolayer in magnetic field that it's a trivial insulator. There's no edge state. And this is, for example, the state that appears when you put graphene aligned with boron nitride and you apply a magnetic field. So in that situation, a charge density wave appears, which essentially means that you have more electrons in the A sublattice than in the B sublattice. And that charge density wave gives rise to a quantum Hall state that it's actually trivial because you happen to fill the right or wrong Landau levels, depending on how you think about it. And then, of course, there's another alternative, which is the alternative in which you fill other Landau levels. And when you fill those other Landau levels, you may end up with actually a total Chern number of the occupied states that is non-zero. And in that situation, you essentially get gapless chiral states. So in these two situations, you both you have 2 filled Landau levels and 2 empty Landau levels. The only difference is that you are changing which ones you fill and which ones you empty. And depending on which ones you fill and which ones you empty, that you can control by the substrate or by external perturbations, you can have a trivial insulator or a different type of Cherninsulator. And this is going to be also important later on. All right, great. So now let me show you a couple half-filled Landau levels that both are equally trivial, but they are trivial in a different way. The first one is the charge density wave that I showed you before, that appears when you put graphene on top of HBN. And then the one on the right is the antiferromagnetic state, which essentially means that you put up electrons in sublattice B, in sublattice A, down electrons in sublattice B. So you have the same number of electrons in both sublattices, but just in one sublattice you have all up, and on the other sublattice you have all down. So this is very much like the antiferromagnetic states that we were discussing in the magnetism session. So these two states, they are, let's say, topologically trivial in a sense that they have a gap, and they have no gapless edge states, but they are actually appear in different situations. So if your HBN is aligned, you drive the first. If your HBN is not it's not aligned, so it's twisted with respect to graphene, then you are in the second situation. And in particular, when you apply a magnetic field to this second situation, in particular, very large in-plane magnetic field, you get to a quantum spin Hall insulator, as we will see. All right, great. So for Landau levels and for edge states, you have the very same phenomenology of seeing both bulk states and edge states, depending on which energy you look at. So, for example, if you are right at charge neutrality, and let us now assume that we don't have interactions now, then all your states live in the bulk of your ribbon, that it's infinite in the x direction. Now, if you start changing your chemical potential, so the filling of your system, you start crossing your edge states, and your edge states live now on the edge, of course. And then if you start increasing the chemical potential more and doping your system more, you again hit another Landau level and your states start living again in the bulk. So as you change the chemical potential in a quantum Hall state, you are all the time going from edge states, bulk states, edge states, bulk states, and so forth, which essentially means that you are filling more and more Landau levels. All right, great. And now let me show you something that is actually very nice. So we were discussing in the previous session that we have some of these systems that realize Chern-insulators in which we have chiral edge states, let's say, in the absence of a magnetic field, just because there's some spontaneous breaking of time reversal symmetry. So those states had, let's say, one state propagating in one direction, one edge, another state propagating in the other direction on the other edge. So what you can actually show is that this state is essentially topologically equivalent to a quantum Hall state. And the way in which you can do it is just by doing the transformation explicitly between this Hamiltonian and a quantum Hall state. So here what I'm showing you is how you can go from a Chern insulator without magnetic field to a quantum Hall state in which your edge states smoothly transform onto the edge states of a quantum Hall system. And of course, your bulk starts developing Landau levels. So in other words, the quantum Hall effect or the quantum Hall state is actually topologically equivalent to a Chern insulator. The only difference is that in one you have magnetic field, in the other you don't have magnetic field, but essentially you can transform one onto the other without closing the gap in the bulk and without destroying your edge states, of course. All right, good. So that is everything that I wanted to tell you about monolayer graphene. Now let us look at twisted multi-layers, and in particular twisted bilayer graphene. So before I was telling you that we could do this mapping between, let's say, Landau levels and quasi-periodicity, or Landau levels and Moire patterns. And twisted graphene bilayer, it's actually one of the nicest examples of this. So if you take the two layers of graphene at an angle close to 1 degree, your electronic structure looks like this one. So it looks like a very, very flat band. And this is the magic angle flat band. This flat band is actually a Landau level by itself. It is a Landau level that it's not driven by a magnetic field, because of course there's no magnetic field here, but it's a Landau level that it's driven by a modulation in space. It's a Landau level that it's driven by the change of the interlayer hopping in space, that it's of course driven by your twist angle. And in particular, this Landau level can be mapped both to a high-dimensional quantum Hall state, of course, but it can also be mapped to a two-dimensional non-abelian gauge field, where the non-abelian nature is essentially the sublattice degree of freedom. So for us, what is going to be important is that as a Landau level is going to have a Chern number. So something that is very important for many of these twisted bilayers is that the flat bands have finite Chern numbers. Of course, the total Chern number of your electronic structure is 0, right? Because you have both, let's say, K and K prime, and in particular, you don't have any magnetic field. So if you don't have any magnetic field and you don't have any term that breaks time reversal symmetry, the total Chern number of your system must be 0. So what actually happens is that in these flat bands, you actually have 4 different flat bands, and you have 2 flat bands that have Chern number -1, another 2 flat bands that have Chern number 1. So if you are in a situation in which you don't spontaneously break the symmetry, your Chern number is always going to be 0, which is what happens in the absence of interaction. So this is just a direct consequence that the let's say pseudo gauge field here that gives rise to the pseudo Landau levels is an elastic gauge field. It's a gauge field that doesn't break time reversal symmetry. But of course, you can start thinking about what happens if you start reordering your Landau levels in the very same way as we were doing in monolayer graphene before, when introducing interactions. And in particular, in twisted graphene bilayers, you can get to a situation in which interactions alone decide to fill 1 of your flat bands and leave, fill 3 of your flat bands and leave empty the other flat band, so that the total Chern number that you get is 1. And this is something that, of course, happens very close to the magic angle, because you need these ultra flat bands. And it happens also when you have an HBN encapsulation in which one of the HBNs is aligned with your twisted bilayer. And the reason why this is important is because otherwise you wouldn't be able to lift the degeneracy between the Dirac points. So are you thinking about the orbital part of the magnetic field or the Zeeman part? More the Zeeman. So in principle, it shouldn't be hard. Of course, what may happen is that since your band is very flat, it becomes correlated, and your magnetic field needs to kind of win over this correlation, right? So if, for example, your flat band gets correlated and gets a gap of 5 MeV or so, then you would need to apply a very, very large magnetic field to be able to overcome this 5 MeV. But if you manage to have a flat band that it's not correlated, you could, of course, split it with a magnetic field. And of course, that is something that you could do also with a magnetic encapsulation. So if you do put a 2D magnetic material below your system, just the exchange coupling alone can create this splitting. Yeah, great. Thanks. That was a very good point. All right, great. So the important thing for us is that the flat bands of twisted bilayer are pseudo-Landau levels. And if we have both the alignment with HPN and also interactions, and of course the right filling, so that we feel free of the Landau levels and not the fourth one, we essentially get a Chern insulator for free without actually having to apply an external magnetic field. And let me emphasize that this is maybe one of the most interesting phases realized in twisted graphene bilayers, because there are extremely few Chern insulators in nature. So there are 2, maybe 3, depending on how one counts. And twisted bilayer graphene is one of them. And what is most important is that the quantization of the conductance that one gets in these twisted graphene bilayers that become Chern insulators by themselves is extremely good, and it's actually even better than some other proposals, some other experiments. All right, good. So that is the important thing. And now there's another important issue here, which is that you may have heard about something called fractional quantum Hall effect, which is essentially a situation in which instead of having integers of conductance, you have fractions of conductance. So there are many different fractions, and depending on what is the filling of your Landau levels, you get one or the other. So fractional quantum Hall states appear when you start doping a Landau level. So when you don't have an integer number of Landau levels filled, but just a portion of them. So let's say 1/3 or 2/3 of many other different fractions. And that usually requires extremely large magnetic fields because you need to have both Landau levels and very strong correlations. In twisted graphene bilayers, and in general, in twisted graphene multilayers, you have flat bands that are Landau levels for free without magnetic field. What this actually means is that in the very same way that you are getting Chern insulators at zero magnetic field, it may be possible to get fractional Chern insulators at zero magnetic field. And now let me note that fractional Chern insulators at zero magnetic field have not been found yet in twisted bilayer, but fractional Chern insulators are at really low magnetic fields. Fractional Chern insulators filling, let's say, that appear when you fill this structure with the right filling have been found experimentally. And the current understanding is that where this system is extremely close to be a fractional Chern insulator. And when you apply a magnetic field, what you are doing is just giving the last push that the system needs. So in other words, if you take the right filling in these twisted graphene bilayers and you align them with boron nitride correctly, and maybe you add a little bit of strain, maybe you add some gate around, maybe you may be able to create a fractional Chern insulator at zero magnetic field. And that would be state of matter that has not been so far in nature. Fractional Chern insulators have not been found in any material so far. Fractional quantum Hall effect, of course, has been seen, but fractional Chern insulators at zero magnetic field have not appeared. And this very same strategy is, of course, being pursued in twisted graphene bilayers, but it works in many other twisted graphene multilayers. So if you think about the twisted double bilayer that we discussed yesterday, the flat bands in the twisted double bilayer, they also have finite Chern numbers, and they also give rise to Chern insulators, and they can also potentially give rise to fractional Chern'insulators. And in general, all the flat bands in twisted graphene multilayers have finite Chern numbers, which is something essentially that is inherited from the Dirac nature of the graphene electrons.
There, can I ask a question about
yes.
This, you say that the it's ability for the fractional this future ones. What is the role of this APN in calculation? I didn't quite get it because I thought that you can also just have a spontaneous unit rate driven by interactions.
Oh, yeah, that's a very good point. So the point is that you have a Dirac point here. So the different Landau levels are kind of linked to each other by a Dirac point. So even if you try to split them, since you have a Dirac point, you can't, right? Because they are linked through this Dirac point. So you need to destroy this Dirac point to get a Chern-insulator, because otherwise, yes, exactly. So the role of the ABN, of the HBN, is to break the AB symmetry. Because I mean, of course, I drew the Landau levels like this as, let's say, disconnected bands, but what actually happens is that in the absence of HBN, there's a degeneracy between all these states that is protected by inversion symmetry. So if you don't break inversion symmetry, then you are not capable of making this splitting. In principle, no. I mean, you don't have degrees of freedom left, let's say, to break this spontaneously, because I mean, this breaking here is breaking of Waal's symmetry. So yeah, I mean, you can either break Waal's symmetry or break inversion symmetry, but not both of them. And of course, there's a spontaneous breaking of inversion symmetry in some twisted graphene multilayers, but exactly. But in those cases, you don't get Chern-insulators because you chose the wrong Landau. I mean, not the wrong Landau levels, but a different set of Landau levels to fill. So you need to break inversion symmetry by hand, and once you break it by hand, then your twisted graphene bilayer decides to fill just one of the valleys.
Another question here is that then this means that this breaking of the size of the breaking of the inversion matters.
Yes, it matters.
Parameter that describes size.
Yeah, I mean, yes, it matters.
It either works or it doesn't. You know.
Yeah, the size, of course, the size of the symmetry breaking matters. So, of course, let's say the typical energy scale is this splitting over the inversion symmetry breaking. So the inversion symmetry breaking that you need is, let's say, on this order or smaller, but that is exactly what you have in the experiment, actually. So HBN encapsulation, and when you align HBN with graphene, creates a splitting in the Dirac point on the order of, let's say, 510 MeV, which is actually even much bigger than what you need for this splitting in Chern-insulators.
Not the combination of parameters. That's what it is.
Yeah, exactly. It is the value that it is, but it is the right value to get this. So it is bigger than the splitting that you get for your Chern-insulator. All right, great, wonderful. So let us now move on to quantum spin Hall insulators, and in particular to van der Waals quantum spin Hall insulators. So the next topological state of matter is actually relatively similar to the quantum Hall states and Chern insulators that we thought before, but a little bit different. So the basic idea is now that in quantum spin Hall insulators, instead of having just one state that propagates in one direction, now you have one state that propagates in one direction and one state that propagates in the opposite direction. But what is important of these states is that they have, let's say, different component of the spin in the z direction in the simplest model, and in general they have opposite helicity, and they are time reversal partners. What this actually means is that if you take the wave function of this electron and you apply time reversal symmetry, you obtain the wave function of the opposite electron. So if you think just in a pictorial way, when you see this picture, you can just think that, well, we just actually just make two copies of a quantum Hall state or two copies of a Chern insulator. We take a Chern insulator we take the opposite Chern insulator for the blue spin, we put them together, and we essentially get a quantum spin Hall insulator. And even though that seems like an oversimplistic picture, that is actually a very good picture to understand quantum spin Hall insulators. So essentially, let us just compare Chern insulators with quantum spin Hall insulators. For Chern insulators, we need to break time reversal symmetry. We have chiral modes, and the reason why we need to break time reversal symmetry is because if you apply time reversal symmetry to this picture, you get the opposite picture, and therefore, if you have time reversal symmetry, that you cannot have states that are chiral. But now, if you look at this picture and you apply time reversal symmetry, then you recover the same picture, because time reversal symmetry changes the direction of propagation of your states, but it also changes the spin. So once you switch, let's say, the direction of the arrows and the color, you recover the very same picture. And therefore, a state like this respects time reversal symmetry. And of course, in quantum spin Hall insulator, instead of having chiral states, we have helical states. And by helical, what this means is that each spin direction propagates in an opposite direction, or each, let's say, member of a Kramer's pairs propagates in the opposite direction. All right, so first, let me show you one very simple way of getting a quantum spin Hall insulator, which is actually just by taking the quantum Hall state in graphene. And this idea relies just on, again, taking the 4 zero Landau levels and ordering them in the right way. And by right way, I just mean that the up electrons are filled so that you get a positive Chern number, and the down electrons are filled so that you get a negative Chern number. And what this actually means from the point of view of your order is that you got to a ferromagnetic state. So all the up electrons, let's say you fill all the up electrons and not all the down electrons in the zero Landau level, or the other way around. So for example, if you start with the anti-ferromagnetic state, that was topologically trivial, as we described before, you can essentially go to the ferromagnetic state just by counting your moments. So now the basic idea is that if you think about this monolayer graphene when it's not aligned with boron nitride, when you apply an out-of-plane magnetic field, this is the correlated state that you get. So an anti-ferromagnetic state that has a gap. So quantum Hall graphene in a magnetic field has a gap, actually. And this gap is essentially driven by correlations and realizes a state that is essentially an anti-ferromagnetic state. Now you can start applying a very, very large in-plane magnetic field. And the idea is that an in-plane magnetic field couples to the spin degree of freedom, but it does not couple to the spatial degree of freedom. And when you apply this in-plane magnetic field, you essentially start adding more and more Zeeman energy to the system, so that eventually, instead of being anti-ferromagnetic, it decides to be ferromagnetic. And when it becomes ferromagnetic, you essentially get your Landau levels ordered in this way, and one of the channels propagates in one direction, the other channel propagates in the opposite direction. And let me emphasize that this is, of course, something that has been done experimentally. So there have been experiments showing that at zero in-plane magnetic field, you get a gap. And as you apply a large magnetic field, you get, let's say, helical states. Of course, the in-plane magnetic field that you have to apply is relatively large, something on the order of 20 Teslas or so, because you need to overcome the interaction energy. But you can actually realize quantum spin Hall insulators in graphene. And what is important, without any sort of spin orbit coupling. Now, you may wonder, well, hold on. You actually mentioned that for having quantum spin Hall insulators, we needed time reversal symmetry, right? And here we are clearly breaking time reversal symmetry. So this is, so there's something that does not seem to match. So the basic idea here is that this quantum spin Hall insulator is a special type of quantum spin Hall insulator that it's actually protected by the conservation of the spin in the direction of the magnetization and not by time reversal symmetry. So the topological invariant that one associates to this quantum spin Hall insulator is the spin Chern numbers, the difference between the Chern numbers of spin up and down. And as long as you introduce perturbations that do not create spin mixing, and perturbations that create spin mixing are spin orbit coupling or non-collinear magnetization, or magnetization perpendicular to your direction, and so forth, then you have a quantization. And it turns to happen that in these samples in which they apply large magnetic fields, one doesn't have large spin orbit coupling because, of course, it's graphene, it's very light. and one also doesn't have non-collinear magnetization once you enter the ferromagnetic state. All right, good. So that was, let's say, the simplest type of quantum spin Hall insulator. So for now, let us move on to see how we can engineer a quantum spin Hall insulator that actually has time reversal symmetry. So let's see what are the ingredients that we need to find a two-dimensional material that realizes that. And let me emphasize that, of course, there's a 2D material that realizes quantum spin Hall effect, that it's 1T prime tungsten ditelluride. So the basic idea is that we start with the idea of a Chern insulator. So this state that has chiral edge states and it has a finite Chern number, and that the Chern number essentially stems from the very curvature. So now the basic idea is that if you think about the simplest model for a, let's say, Dirac equation, or the simplest model for a honeycomb lattice, you can actually have two different situations for the gap that opens up. You can have a situation in which the gap that opens up is a topological gap, namely that the two Dirac equations give rise to have the same sign of the very curvature. That is what you see here in reciprocal space. Or you can have the situation in which the signs of the very curvature in the different Dirac equations is the opposite. To get a quantum spin Hall insulator, what you actually need is that this picture appears for spin up, and the opposite picture appears for spin down. What you need to get a quantum valley Hall insulator is this picture, essentially, that one valley has positive very curvature and the opposite valley has the opposite very curvature. So having a very curvature that is spin dependent is something that can be engineered by spin orbit coupling, and that it's driven by spin orbit coupling. And having a very curvature that changes in between valleys is something that is driven by an electric field in a bilayer graphene or by a sublattice imbalance in a monolayer graphene. So the idea is that for the Dirac equation, you essentially have that the Chern number of each valley depends on the sign of the mass in that valley, and also in the, let's say, sign of this K here that essentially tells you if you belong to one valley or you belong to the other valley. So the basic idea for quantum spin Hall insulators is that you get valleys of masses of opposite sign for opposite spins, and with the same sign in the two valleys. So if you think in terms of Chern numbers of the up channel and the down channel, a quantum spin Hall insulator is essentially characterized by having a total Chern number that is 0. So different spin channels have different Chern numbers. And of course, this is going to be the case because you want states that propagate in the opposite direction. But then once you consider the difference between Chern numbers, the difference between Chern number in the up channel and Chern number in the down channel, you essentially get a finite number, and in particular, plus minus 2. So the set 2 invariant can be understood as whether if your Chern number is 0 or your spin Chern and your spin Chern number is 2. So in other words, if you have spin Chern number equal to 0, your set 2 topological invariant is 0. If you have spin Chern number equal to plus minus 2, your set 2 topological invariant is 1. And let me emphasize that for computing the topological invariant of quantum spin Hall insulators, one usually doesn't think so much about the spin Chern number, but directly about the set 2 invariant. But the point is that let's say computing the set 2 invariant is a little bit more complicated than computing the Chern number. It can be done by pumping the Bannier functions in a path that is time reversal symmetric in the Brillouin zone, or have the Brillouin zone, but it has an interpretation that is a little bit more complicated than the Chern number. But for this very simple model in which we think that we can separate the Hamiltonian into up and down channels, one can just think that one has opposite Chern numbers for opposite channels. And of course, what is most important is that these spin-dependent masses are generated by spin orbit coupling. So in principle, graphene by itself is a quantum spin Hall insulator because of its intrinsic spin orbit coupling. But the spin orbit coupling gap in graphene is really, really small. It's something on the order of 20 microelectron volts, maybe 40 microelectron volts. So let's say way below that the usual temperatures that we are used to in other states. But of course, as you go to materials that are heavier and heavier, then spin orbit coupling contribution becomes stronger and stronger, and eventually it can actually be large enough so that you can see it experimental. So in particular, in this compound that I mentioned, so 1T prime tungsten dichalcogenide, one can see quantum spin Hall effect up to 100 Kelvin. So it is not room temperature, but it's a really, really large temperature for a quantum spin Hall insulator. And of course, the reason for that is because tungsten is a really heavy element, and the heavier the element, the stronger the spin orbit coupling. All right, so this is essentially the picture that we have. So we want Chern number 1 for one channel, Chern number -1 for the other channel, and essentially the idea is that spin orbit coupling essentially is capable of generating a mass that is spin dependent, or if you want to think in terms of internal magnetic fields, you can think that this term in the spin orbit coupling, Lz times Sz, generates a magnetic field that is spin dependent. So this is a very simple way of understanding why spin orbit coupling drives quantum spin Hall states, which simply comes from the fact that the angular momenta can be thought as an internal magnetic field, and the spin orbit coupling essentially creates an internal magnetic field that is spin dependent. And of course, what we have in this quantum spin Hall insulators is that the different spins propagate in opposite directions in the sample. And when you look at an electronic band structure, you essentially see something like this. So you see a crossing between the up channel and the down channel. So this crossing, let's say, appears, and it is related with states that live on the same edge. But the idea is that this crossing is actually protected. So if you want to open up this crossing, you need to break time reversal symmetry. And from the point of view of the electronic structure, what this actually means is that these crossings are always going to appear in time reversal invariant points. So either in the gamma point or in the X point. And at those points, you have something called Kramer's degeneracy, which is the idea that when you have fermions, essentially every single eigenvalue must be twofold degenerate in the points in the Brillouin zone, which are their own time reversal symmetric. And this, of course, holds in the presence of spin orbit coupling. And this, of course, holds in the presence of even spin orbit coupling that breaks your whole spin rotational symmetry. So in the presence of Rashba spin orbit coupling or any other spin orbit coupling. And that is the reason why these states of quantum spin Hall insulators are completely resilient towards, let's say, any kind of non-magnetic disorder or any kind of spin orbit coupling, because all those perturbations do not break time reversal symmetry, and Kramer's degeneracy alone guarantees that there's going to be a crossing there.
One question about comparing these ordinary quantum Hall insulators between in the ordinary ones, you don't have an external magnetic field. You don't need it. I mean, you have coupling, which actually means that the spin gradient is not valid. So the states are helical in some bases, but then let's say you can assume that you inject the spin into this edge states, the spin gradient does not stay, so that you cannot assume that at some point further away the same spin. So in graphene, I guess this is not you. I think you will show that you need a magnetic field
to get the quantum spin Hall state.
Yeah, they're kind of more robust.
Yeah, that's a very good point. So let me ask for the first point. So in general, when you have spin orbit coupling, of course, you no longer have a good direction of the quantization of your spin. So if you insert a spin in one direction, it is probably just going to let's say, change as the spin moves in space just because of the spin orbit coupling itself. In some very specific fine-tuned models, you actually have still a conservation of one of the spin directions. So for example, the quantum spin Hall state in graphene in the absence of magnetic field, so this one that has a 20 microelectron volt gap, actually conserves the SC direction of the magnetization. So spin orbit coupling does not mix an electron that enters as a spin up. So an electron that enters spin up will always remain as a spin up. And this stems directly from the specific symmetry of graphene. Now, if you start, for example, breaking mirror symmetry at rush spin orbit coupling, so this conservation already disappears. So for very fine-tuned models, you can have conservation of the spin, meaning that you can think that your spins move, that your spins point in a very specific direction, and that this very specific direction is going to be conserved in space. Of course, for generic topological insulators or for generic quantum spin Hall insulators, that is not going to be the case. So, of course, in this case, that it's the most relevant one. Experimentally, there's no good quantization axis in principle.
The idea of really this stuff and that stuff is
yeah.
This
Absolutely. So, and then coming back to the spin Hall driven by magnetic field, of course, in that case, let's say if you happen to have some spin orbit coupling somewhere, then that's not good. So the quantum spin Hall in state driven by magnetic field is good as long as you don't have spin orbit coupling. But if, for example, your substrate induces some spin orbit coupling, then it's going to destroy your helical edge state. So these two strategies have, let's say, both advantages and disadvantages. So the one has the disadvantage that maybe you don't have a good spin quantization of the spin direction. The other one has the disadvantage that maybe is, that it is going to be less robust with a magnetic field. Yeah, great, thanks. That was a very good point. All right, great. So now let us look at how these quantum spin Hall insulators behave when we apply or when we include disorder in the model. So we start with a quantum spin Hall insulator that is absolutely clean. And if it is absolutely clean, then we have our helical edge states that are protected by symmetry and that appear closing the gap. If you now start adding disorder in the system, and in particular non-magnetic disorder, will you actually see that, yeah, I mean, the dispersion of your states is going to change, but your gapless states are going to remain there. And in particular, this crossing that appears at this time reversal invariant point is not going to disappear. It may move up in energy, down in energy. Maybe the slopes of your edge states are going to change, but the edge states cannot disappear because you have Kramer's degeneracy, and this Kramer's degeneracy holds irrespective of if you have disorder, irrespective if you break all the translational symmetries or all the crystal symmetries. So as long as you don't break time reversal symmetry, these states are going to remain there. But of course, if you now start adding this disorder, that it's magnetic and therefore breaks time reversal symmetry, then you very easily can lift the degeneracy between these edge states. So you can very easily open up a gap. And this is, of course, something that you will be doing today afternoon in the exercise session. All right, great. So I think that now it's a good time to make another break. And what I would ask you during the break is to think about which one of these two configurations represents the right interface between a quantum spin Hall insulator and a Chern insulator. And again, of course, please go outside, get